Hello, I am AJ Montgomery, software engineer for Signal Hound. In this video, we will be taking a look at the BB60C, a 27 MHz real-time spectrum analyzer. The BB60C is USB powered and connects directly to your PC or laptop running Windows 7 or Windows 8. The BB60C is a high-performance and affordable spectrum analysis and spectrum management solution.
The BB60C offers various spectrum measurements, measure out-of-band emissions, and check transmitter faults with channel power and adjacent channel power measurements. Ensure carriers are within assigned channel bandwidths using occupied bandwidth measurements. Identify interfering signals and short-duration transmission bursts with the persistence and waterfall displays, and then characterize PLL overshoot and settling time using zero-span. Capture short-term spectral events, such as PLL transients, using real-time spectrum analysis. Add up to 6 traces and 6 markers to any configuration.
Today, we will be taking a look at the differences between real-time and swept spectrum analysis and performing a number of measurements on a live Bluetooth signal from a wireless mouse. We will show you how to use the BB60C to identify, characterize, and analyze a signal of interest. Our setup today includes a broadband antenna connected to the RF input of our BB60C. The BB60C is connected to our laptop via USB 3.0, running our spectrum analysis software.
Now I have launched the software. The device is sweeping the default span of 11 MHz to 6 GHz in about a quarter second. The fast sweep speed of the BB60C lends itself to high probability of intercept interference hunting and EMC pre-compliance. You can use the sweep settings control panel here on the right to change center frequency and span, reference level, resolution and video bandwidth, detector settings, and sweep time. The measurements control panel on the left provides controls for traces, markers, channel power, and occupied bandwidth. There appears to be some intermittent signals around here. Let's add a max hold trace to capture several of these events. We do this by selecting Trace To and Max Hold. As the BB60C captures these signals, the max hold trace stores their peak amplitudes. Once we have captured some of these events, we can place a marker on the max hold trace by selecting Trace To and Peak Search. The marker readout here shows us the frequency and amplitude, in this case 2.42 GHz. This frequency is within the 2.4 GHz ISM band and is most likely our Bluetooth signal. Now let's narrow in on this signal by setting our center frequency to 2.45 GHz and span to 100 MHz. We can see our Bluetooth signal hopping through much of the ISM band. Since max hold is still on, we are accumulating several evenly spaced hops through the spectrum. Now let's use delta markers to measure the frequency spacing of these hops. To accomplish this, peak search, delta, and then peak right. The delta readout shows spacings of about 1 MHz, which is consistent with the Bluetooth signal. We can view the hop pattern with the spectrogram or waterfall display. Each horizontal line in the display represents a sweep where the color spectrum is used to indicate the amplitude. For those people who prefer a 3D topographical view, this is also available. Currently, we are sweeping this 100 MHz spectrum every 10 to 20 milliseconds. While we can see all the frequencies used over time, this does not really give us a clear picture of how often packets are being transmitted on each frequency. In fact, no traditional spectrum analyzer can convey this information. It takes a real-time spectrum analyzer like the BB60C to capture this information. Entering real-time analysis mode is as simple as selecting Analysis Mode and Real-Time. Immediately, we notice the spectrogram is filled with activity. This is because real-time gives us continuous, gap-free coverage of up to 27 MHz of spectrum. Every Bluetooth transmission will be captured and displayed when you're in real-time mode. The persistence display is activated by default when entering real-time mode. Persistence superimposes multiple traces showing more frequent signals as red and less frequent signals as blue. New Bluetooth packets appear bright and then fade over time. The software includes the ability to record the spectrum being displayed in swept or real-time mode. Pressing record immediately begins the capture of incoming sweeps. We could record for hours, but we only need a few seconds, so let's stop here. The file is now ready to be played back in the software at any time. Pressing play allows us to select the file we just recorded. Playback begins immediately. We can press pause, rewind, and single step through the sweeps we captured. We can now perform additional measurements on this recorded signal. Viewing the signal in the frequency domain is useful for many measurements, but some measurements can only be done in the time domain. Using ZeroSpan, we can view the packet timing and modulation characteristics of our Bluetooth signal. I've created a preset with everything already set up. I've set the center frequency to 2.44 GHz, bandwidth to 1.2 MHz, sweep time to 200 microseconds, and enabled video triggering. Let's hit single trigger and grab a packet. ZeroSpan has 3 separate plots. The top view shows us the demodulated waveform. In the lower left, we see the spectrum of the time domain capture, and in the bottom right, the IQ waveforms are displayed. We have captured our packet. Now let's see what we have. We are currently viewing amplitude versus time, or AM. This shows us the instantaneous power for each sub-microsecond sample. Let's place a marker to measure the packet transmit time. It reads 142 microseconds. The amplitude on this packet is pretty flat, as you'd expect with Bluetooth. So let's take a look at frequency versus time on this same capture. Now we can see the Gaussian FSK modulation of the Bluetooth packet. From here, we can use our markers to take a few measurements and characterize the modulation. It looks like the Bluetooth access code starts with a nice 1-0 sequence we can use to measure the peak-to-peak modulation and symbol rate. Placing a marker and delta marker, we can see the peak-to-peak deviation is 272 kHz and the time delta reads 1.2 microseconds. We can measure the symbol rate more accurately by moving this delta to this peak here 10 symbols away. It reads 10 microseconds, so the symbol period is a tenth of this. Using this value, we get a modulation rate of about 1 megabit per second, the expected rate for a Bluetooth access code.
I hope you have enjoyed this demonstration. The full span sweeps, real-time, and zero-span analysis we have shown you today apply to a broad range of signals, making the BB60C well-suited for many applications, all at a price you can easily afford. For more information, visit www.signalhound.com today.